All right, so we in the previous videos had looked at this expression, right? And we took this as a definition that this was the volume of the solid that exists between the xy plane and the surface expressed by this function, with the caveat that it could be negative. We didn't really get into how we might actually compute these things, okay? So that's what we want to do here. So we're going to start with an equation that we'll have to dig into to see what exactly we're getting at. So let's look at this equation. I'm defining the function a of x to be the integral over the function f of xy dy over this interval CD. So let's see exactly what I mean by this with an example. Suppose I had f of xy is equal to x times y. And let's take the interval CD to be 0, 1. Just keep it simple. Then a of x is equal to the integral from 0 to 1 of x times y dy. And so if I compute, for instance, I could compute something like a of 2. That means put 2 in for x, I get 2y dy. And now notice this is simply an integral with respect to y. We could use all of our regular rules to evaluate this. And we see that we get 1, right? Y squared evaluated from 0 to 1. We get 1. So this is just to show that this makes sense, right? That we can define a function in this way, because it might look a bit confusing when we first look at this. But this is what we mean. We pick a value for x. It's a constant now. And so we can evaluate the integral in terms of y because x is a constant, okay? And it spits out a number, which means, as stated, a of x is a function. Well, what can we do with functions? We can integrate functions. I can integrate the function a of x from over some interval. It's a function of x, right? I input of x, output a value. I can integrate this thing. But what does it mean? That means now I'm just substituting what a of x is into this piece of this, and it looks like this, okay? So what is this expression saying? It's saying, well, to evaluate this integral over this function a, you take the integral f of xy with respect to y, right? Just like we did over here, you could evaluate this because x itself is a constant with respect to y, right? So we integrate over y, then we get something, we get an expression in x that we can then integrate with respect to x. So for instance, let's go back to this example I did. Let's say we just wanted to do something a little bit differently. And instead of putting in a value of x, oops, that should be a y, I'm remembering that x just represents some constant. And so no matter what value I put in for x, I know what's going to happen here. I'm going to do this integral with respect to y. So I'll get 1/2. X will just be a constant, and we'll get 1/2 y squared evaluated from 0 to 1. Or x times 1/2, right? Or maybe it's nicer to write 1/2 x. Doesn't really matter, right? Notice a of 2, if I put in 2 for x, I would get the 1 that I got up here. And if I put in any value of x, it's going to be treated like a constant, just like we treated it as a constant here. And so we're just letting it represent all the possible constants it can be. And so in terms of y, it's treated as a constant. So here, the same thing applies. Whatever happens with x, we can treat it like a constant, take the integral with respect to y. What do we end up with? Well, look what we ended up with here, a function of x. And then you do an integral with respect to x, right? So we're doing the inside first, then the outside. So we usually don't write these brackets. What you'll often see is an expression like this, okay? And what this is giving us, well, let's come back to that. We call this an iterated integral. And the way we compute them is, as I said, we start with this inner integral, we treat x as a constant and integrate with respect to y, then we get to the outer integral and integrate with respect to x. So let's do an example of how this works. Oh, I should also mention, there's no reason I couldn't do this in the other direction and get an iterated integral of the form c d a b f of x y dx dy. Right? There's no reason I couldn't do this start with a function of y and play the same game. So there's nothing special about the order I did it in. So let's do an example and then come back to what this means a little bit. So let's look at the following iterated integral. 2, 3, 1, 4. I'm going to stick with the function x times y dy dx. So I work from the inside out. So first I'm doing this integral with respect to y. So I'm focusing on this piece of it. The other stuff is sort of acting like it's just containing it, right? So this looks like that. So with respect to y, I get x over 2 y squared evaluated from 1 to 4. Remember, these are y values. So that's what this internal, the inside integral ends up looking like. So I still haven't done the x integral. I have to finish evaluating this. Remember, from x, these are x values. So I get x over 2 times 16 minus 1. And then we have dx. So we end up with 15, from 2 to 3, we'll have 15 halves x dx. Right, so I did this integral with respect to y. X is treated like a constant. You can slide it out if you want. All of our regular rules for constants apply. And now I have a second integral to do. The antiderivative of x is x squared over 2, so I'm going to get 15 over 4 x squared evaluated from 2 to 3, which is going to be 15 over 4 times 9 minus 4, which gives us 75 over 4. Okay, and that's the value of this iterated integral. Okay. Now, let's try something else. Let's try the same integral, but I'm going to switch the order. In other words, I'm putting the x integral on the inside and putting the y integral around it. Let's see what happens now. So again, I'm doing this inner integral with respect to x. The antiderivative of x is x squared over 2, so I get y over 2 times x squared evaluated from 2 to 3. So this becomes y over 2 times 9 minus 4, or 5 halves y dy. Now I do my y integral. I get y squared over 2 again, so this is going to look like 5/4. Y squared, oops, I'm taking the integral, pardon me, let's do that again. So I've taken the antiderivative and I get 5/4 y squared evaluated from 1 to 4, which gives me 5/4 16 minus 1, or this is 15 times 5, or 75 over 4. Okay. So there's an obvious parallel here, right? This is not an accident that these two numbers ended up being the same. Okay. So what this all works out to is the following theorem. Okay. This is something called Fubini's theorem. We'll say if f is continuous on the rectangle R is equal to xy in our xy plane, such that x is between A and B, and y is between C and D. Then those double integrals that we examined in the previous video can be evaluated by taking the integral of this form, this iterated integral, dy dx, or, oops, we can switch the order. Dx, dy. And as long as our function is continuous, these will be the same. And in fact, we can generalize this slightly more. Instead of f is continuous, all we really need is that f is bounded on R, meaning there's a maximum and a minimum, an absolute maximum and minimum value on R, and f is only discontinuous at, what is it, a finite number of smooth curves. And the iterated integrals exist, right? We have to be able to take these integrals. So if all this happens, we now have a way to compute these areas. And for most of the functions we'll be interested in the near future, this is always going to be the case, right? All this condition down here is very similar to when you're taking integrals over a single variable. We can say that f has to be continuous, but if you have a function, right? If I had a function that looked like this, I can certainly compute this integral, right? So as long as it just has a finite number of jump discontinuities. What it can't have, right, is an asymptote, right? Sometimes you can use other methods to compute that with our improper integrals, but they're not always possible. The same thing's happening here. It's harder to draw in more dimensions, but the idea is that if you have some surface, right, it could possibly jump a little higher and do something else over here, and you could still take this kind of integral, right? There's a volume under this one and a volume under this one, and so you're really just adding those two together. So as long as there's not a version of an asymptote, right? We've seen some surfaces where they sort of have this asymptote behavior where the surface goes off towards infinity, or they're not jumping around an infinite number of times, then we'll be able to compute these integrals. Okay, so the proof of this theorem is pretty difficult, but I want to give you an idea of what's happening here by taking a look at Well, let's look at a graph for a second. You might remember from integral calculus doing things like rotation, solids of rotation, where the idea was you have some kind of axis and a shape around that axis. It might change at each point, but if you take slices of it, right, you can find what's the area at each point, right? And you might get a function we used to call a of x, and then you integrate over this function. And it's like you're adding up the area for the whole shape. Well, that's a lot of how you can think about this, right? You're finding the area in terms of one function for a slice, and then integrating over that function across under the whole surface. So the picture of that would be something like, let's create this. So here's a surface. Maybe I want the volume above this region, this rectangle here. So around that region, my surface is just this little tunnel. When we integrate in one direction, the inner integral, what we end up creating is a area function, right? And then when we integrate in the other direction, it's like we're adding up all those area functions as we go along, and cumulatively they give us the volume, right? This is not a precise definition of what's happening, but it's, I think, a pretty good intuitive way to think about it. Now, the area function I have here in this animation doesn't change as we move along. That is a feature of my lack of skills in programming this animating software. Most of the time, this function might be changing, right? The shape will be shifting as we move forward. I just was not able to figure out how to make that happen in time. But that's the notion. I think those problems that usually show up in an integral calculus course with those volumes of rotation, one reason those are in there is, I think, prep for this idea that this notion of these areas that are changing along the way, and when you think about those approximating slabs, we can think of the same kinds of things, here. Okay. So that is how we evaluate those integrals. It's the reverse of derivatives. You take the regular old integral of y, treating x as a constant, right? And you treat it exactly as a constant. If you're ever not sure what to do with it, put the number 7 in there, see what you do with the number 7, do that with the x, right? That's exactly what you do with it. And then you take the x derivative, or vice versa. Just like with derivatives, we just have to train our eye, like partial derivatives, train our eye to think of one of our variables as a constant while we do that process. Okay, that's it for this one. I'll do an example or two in some further videos. Thanks, everybody.